Okay. Okay, so for today's class, I think I will just finish off some of the subtopics on chapter 3, the axial deformations. So we're going to start with the axial deformation on a non-homogeneous member. So non-homogeneous means that it will have a different property. For example, we have this bimetal bar. So we have two members that is joined together, and it has different E. So it has different stiffness. So we call E1 and E2 for these two metallic bar, and then we need to calculate the locations of the resultant force, and based on the structure, it has all this height and base, and it is determine the centroid of the resultants P. And then assumptions are the E2 is greater than E1 based on the questions here. So they are two material, they are bonded together, and then we need to calculate the distribution of normal stress that must be applied at each end. So we need to compute the P on that both ends, and it will undergoes the axial deformations. So first is, as you can see the figure 2 on the right side, you see that we have distributions on each metal 1 and 2, and then as mentioned in the questions that the E for metal 2 is greater than E1. So we have the stress, or the normal stress 1, normal stress 2. So we need to calculate both of them. So remember that the basis is we are going to take the stress equal to E multiplied with the strain. Okay? And of course, we need to also consider the dimensions. So which means that the dimensions will have some impact on the calculations for the resultants, especially the centroid. Okay, so now if we go through with what we have here, then the strain, I think, so assuming okay, so we need to assume that the strain is constant. If we not assuming the strain is constant, then we are not going to solve these two equations. So basically we have two equations. The first equation is this for metal 1, and the second equation is for metal 2. So if we are not assuming the strain for both of these materials not the same, or it's not a constant, then we are going to have a difficulty to solve these two equations simultaneously. So the resultants for the force and moment, so we take the F, it's basically integration for the stress, the A, and of course this is with respect to the A. And then we have the My, which means that the M on the y-axis, this will be equal to integrations So we have a stress, and then we have the z. So if we use our right hand, we get the positive y-axis, right? And then we take another one, the mzx. This will result in the negative because the stress, and then you go to from y, and then go to this sigma, you go to the z negative, right? So the mz is negative. And then from the picture, let me write here, the resultant of normal stress distribution is a force acting through centroid. Let me just write this as a note. So you need to think on how the impact of the centroid. So then we could rewrite the free body diagram. Let me make it here. So this will be one. Or maybe let me write with green. Okay, and then the resultant based on these two metals. So I will make from the side view. So remember that we have this h/3 and 2h/3. That is for the total height for each bar. So the centroid, it become half of the h3. So this will be h/6. And let me just write this as a P1. So we can replace the stress distributions by the P1 and P2 for each metal bar. And this will be the P2. Okay. And then we can make this P1 and P2 becomes another resultant in total, which we can rename this as just P, which is our goal. Okay, we need to find the P. And suppose that, assuming that P1 and P2 averagely, it is going to be maybe around here. And we have another terms for this centroid, which we need to know, which is, I will write this as YP. Okay. So this is how it looks like. Okay. So we have a two metal bar, 1 and 2. And each of them, they have different height and different force and different stress. And based on these numbers, we can have their own centroid. But we need to know if they are going to averagely taken into this resultant P, and what will be the height of the centroid. Okay. So that's actually the question. That's the questions. So first, we need to go back to see these P1 and P2 as in the equations, and we assume, remember that we assume that the strain is constant. The strain is constant, which helps us to equaling P1 and P2 in the equations. So first we write the P1 as E1 strain, and then A1, okay, from the F, okay, P over A. And from what we have in our terms, we have the base based on here. The base is just a B, and in the middle part of it is the centroid, B over 2. So for the metal one, we can replace the A with BH over 3, okay, which is height and base. So this will be E1, E, and then this will be BH over 3, okay? And then P2, with the same or similar formulations, we get A2, and for the A2, we have the height 2H over 3. Okay? So 2H over 3 multiplied with B. So that will be the area, which means the cross sections. Okay. Okay, now we get the results for the P1 and P2 from the equilibrium. We just take the X equilibrium, which resulting in P is P1 plus P2, as simple as that. And then the resultant, based on this, then the total P for the P1 plus P2, we can factorize the BH over 3. And then as simply as that, we can simply works as a E1 plus 2 E2. And then we can work this in terms of strain. So let me write one by one. 3P over BH is E, and then this is the Young's modulus. So the strain is 3P over pH, and this will be E1 plus E2, okay? And since the strain is a constant, we can use the strain to substitute to the equations for the stress. Remember the stress we get from here. So let me rewrite here again, or let me just copy. So this stress 1, this will be 3P E1. Oh, wait. This should be here. Okay. Okay. So 3P E1 over pH, and then E1 plus E2. The same one with this one, 3P E2 over pH, E1 plus. Oh, wait. Should be plus 2 plus 2 plus 2. Okay. Okay, now we have another equation. And then to finish off, to get the centroid, the height, the total height for the centroid, we could see the last picture here, YP, and then suppose that we have the whole system. So imagine that these two were in the so both of them, they are in the one picture. Okay, imagine that this is going to have a one picture. So the first one, we take the sigma m, and let's just take the bottom point as our point of view. So take that as a moment. So take this as a positive and take this equaling to 0. So we have P1 2/3 6 P1, and then 1/6 3/6 5/6, right? 5/6 H, and then plus P2 H/3 equal Pyp. Okay. And then from these equations we get that the or let me solve this for a while. Pyp is equal so this is 6 P1 5, and let me write H outside, 5 P1 plus 2 P2, right? So YP is H 5 P1 plus 2 P2 over P. And basically we are going to use all the equations that we know from the P1, P2, and P from this respective equations. So all is this, we substitute all to here, and then finally I will just skip the process here, basically substituting the P1, P2, and P. So we have YP is H and then to get the notes that we only care on YP because the Z is basically the centroid is 0, so we can just use the 2 dimensions here, okay, 2 dimensions diagram. If there is something in the Z axis, then perhaps we need to also include the Z. For example, the moment, okay, the moment where the Z are going to be impactful, like the my here. If there is something in Z, okay, if there is something in the centroid in Z axis, okay. But since there are none, and we could basically say that the Z is 0, or the Z centroid is 0. So basically this is what we expect. So all of these are the one that we're looking for. So we only need to calculate the locations and this normal stress that need to be applied. So this and that. Okay, so this 4. Of course, this is just as assuming that we only have a 2 bimetal bar. But this is how we can conduct the finding the resultant from two non-uniform or different materials. And one particular assumption that is, I think, really helpful, because it doesn't really works in the questions, is assuming this strain is constant. If we are not assuming this a constant, we are going to have a difficulty to make this or to solve it, because if they are all different, there's nothing that can be solved if we not assuming this strain is the same. So that's, I think, will be a basis example, and mostly works for a typical case like this. So every time you have a non-uniform materials that is undergoes axial deformations, the first assumption is the strain, they are going to be the same. If not, then we need to have another method. So we need to make sure that this strain and that strain, 1 and 2, they are going to be the same. Same constant. Okay, so that's the, okay. So that's basically a few subtopics now that I will share with you is basically some of the variations of cases. Okay. So this is in non-uniform axial deformation. And then the next one, okay, if you see, is basically if we have different cross sections, which means that, for example, here we have a column, and of course the column is not the same throughout the length. Throughout its length, the cross section will be different. Okay, so you see the bottom side, the A, and if you walk through A to B, you see that the cross sections are getting smaller. The diameter is different, right? So how do we take it as a problem in axial deformations? And this is another example also for shortening. So we have a column, we press the column, and we expect the column to be shortened. Okay? So we have a P, we press, and then the L should be getting smaller, right? So we need to get the expression for the column under the action of load P. So first of all, since we are going to assume that there will be some small, infinite small elements that is going to be work within the column, and the column will be having a shorten. So instead of having an extension, as we usually take as the deformations, we have a shortening, which the elongations is going to be negative, or in this case I will write as a delta. So remember, we have the elongations, the original equation is this equation E, so we are going to take that as a delta and then take a negative. We know it's negative because the case will be a shortening. So this is because of shortening. Okay, so since we have the delta, then we can rewrite the sum of the axis. Okay. Since I will define the axis x as the vertical, not y, I will write this as x. Okay, to help I think make things easier. Then the f of x is equal negative p, and then this will be constant throughout the diagram. And then, as in for the area, since this is a column, and we know the column will be having a circle in the cross sections, I will define this as area of X. This will be defined as let me just using the diameter, so pi over 4 d squared of X. Okay. So we state the dx, okay, as a variable X, because it will be having a different value. So the area will have different value for each X, right? And then another geometry that is important in our case here is the triangle. This triangle here. So you see that we have the DA here, and you see that this A is different from the top. Let's say we have a DB. So this is DA at A and B, and we have some small gap in which we can define this gap as a DA minus DB. That's our gap, and we can write that as a triangle if you want. So suppose that we have DA minus DB over L, and then suppose that we have a dx in the middle, well, randomly in between A and B. This will geometrically, this will be the same ratio as dA minus dx over X. Okay. So we have two different shape. So this is the green one here, the first shape. Okay, suppose that this is the shape like that. And the other shape is the whole column, okay? Now if we solve this ratio in terms of dx, I will write the final result. So dA minus X over L, and then dA minus dB, like that. So then the A from this dx, we have pi over 4, and the diameter will be dA minus X over L, and this will be squared, okay? And using this area for the integrations, okay, that is what we are looking for this delta. And I will write directly inside the equations. So we are going to generate the A for the area, okay? So write down that this will be, and since the P is constant, right? So we can write, and I will this will be 4P pi E. Well, let me just write what we have actually. So pi over 4 will be 4 over pi, and taken outside, factorized from the integrations, and this will be 0 to L, and this will be dx. And that has having a squared. And basically we need to integrate this, in which we integrate the x. So all the other part, dA and dB, are constant. So basically you will have L, you will have L, and then you can write this will be, this is pi E dA and dB. Okay, that's the, after you get the final integrations. So if you have different cross sections, to review these solutions is basically looking at the different cross section throughout the column. We can relate with the geometry. So first we can relate the diameter, which has different diameter, and we can treat the diameter as a variable, okay, as a variable. And using the variable for the vertical or the height, x. And if you remember, our original equations is basically saying that the delta or the E is equal to PL of AE. Okay. So if we take the dA equal dB, and if, okay, so if dA equal dB equal D, then we have our original equations. Because basically that is giving you the area, right? 4 over pi and then d squared. And basically this is the equation that you can take for the same case. Okay, if you have different cross sections, and you can directly use this one. Okay, this formula. Okay, I think one last case for this axial deformations. Let me go through. So last case is the distributed loading. Distributed loading. So suppose that we have a equations, the equilibrium equations, which we can write as df dx equal minus p of x. So we are going to take x as our variable. X supposed to be the axis that is parallel with our deformations. And suppose that we have this question here. Upon completion of a construction job, the contractor recovers some vertical piles by pulling them out of the ground. So if you can see here, this is the constructions. So we pull with force P out of the ground, and we have for the whole. So if you imagine when we pull this out, every element from this ground, the top ground, until the inside the ground, you have a reaction. When we pull out, we have a reaction which is going to be distributed all the member. And so we have a distributed P. That's why we have the P of x here. Okay. And then it has a length L. And there friction between pile and ground exerts the distributed axial force of px per unit length with the distribution assumed to be shown in this figure. So this is our distribution. So this is our original force. And then when we go through all the length, we are going to have this 3p p0, and this will be going to be linear distribution. So we need to determine the expression for the P0 in terms of the axial force P. Assume that there is no force on the lower end of the pile. Okay. So the F of L is 0. Determine the expression for the internal axial force at the depth x. So that means it's similar to what we have in the chapter 2 or in chapter 1. We slice this, we cut, and then we express this in terms of x. Okay, in terms of x, and then we need to compute the internal axial force. Okay. And then we need to express in terms of P, L, and x. Okay, so first, known info, the F of L at the bottom side will be 0, so no force. And then at 0, at x equals 0, this is equal to P, which means the outside of the ground, right? Outside of the ground. And then we need to describe this in terms of functions. So we have x and px, the axis. And if you feel maybe a little bit confusion, you can rotate this and make px at the bottom side. This is x. So we have px axis and x axis. We can take this into our just some regular linear equations. Okay, let me just write this. So to find the linear equation, so basically we just take the axis, x and bx. So if you look here, if we take a vertical line to this point here, let me just draw a triangle just to make sure that we are on the correct way. So sometimes I think some of geometrical understanding will be making your analysis maybe easier. So if we take this, then we need to write the px is actually p0 plus this part here, right? And let's say this is y. And that y is going to be, we are using the triangle ratio. So if this is p0, this one here will be 2p0, right? So 2p0. So let me write 2p0 over the whole length, which is L, this is equal to y over dx. And then y is 2p0 x over L. So that is our equations. So the px is p0 plus 2p0 x over L. That's our equation. Right? And then remember the equations for the distributions will be df or ddxf is equal to negative p of x. Okay. And basically we take the integrations. So integrate with respect to the dx. Then this will be f of L minus f0 equal minus and then we know that from the informations we have this fl is 0 and f0 equal p, right? So we can write this will be minus p minus, and take the integrations for the p0 plus 2p0 x over L. So this works only for x, right? Only for x. So we have 1 over 2x squared, which we can cancel the 2. So we have p0, and this will be x, right? Plus 1 over L, or x squared over L, right? From 0 to L, right? And this will cancel, which this is giving the p0, or let me just solve this. So L squared over L is L, so this will be 2L. So p0 is 1 over 2p over L. Okay. So we have p0 defined. So this is the first expression, relation p and p0. Okay. Now the second expression that we need is expression for the f. Now apply another variable, let's say the variable t, or a psi, or let me just write t, more easy to follow. So let's say apply the same equations, integration for t equals 0 to t equal x. Okay, because we would like to know what is the exactly the equation for the f of x. So we apply this, then we have f of x equal p. Let me just write the same thing with our original expression. So p minus, this will be the negative px, and let me just exchange x with t to make our integrations, and this will be pt. And then we get the expression for f by taking all the integrations. So this is 1 minus half x over L and then minus half x over L and then squared. Okay, this is after we get through all the result of the integration. So I'm skipping some process here, but I hope you understand how to integrate this. This will give you the t and t squared over 2, and we can cancel the 2, and then we can express the, so remember that, so let me just give you notes here. How we get this is basically integrate and sub the P0 equal half P over L. Okay. So that's how we get it. Okay. So all the P0 is getting half P over L, and then that's how we get the, this is all with P, right? All with P. And that's it for this case. Okay, there is another subtopic, but I think I will just skip that part about wire. I will just skip that. And the next part, still in chapter 3, I believe this is also one of the fundamental aspects in the actual deformations, which is how to calculate. So we have at least 2 methods. Okay, we have 2 methods or 2 cases. We call this statically determinate structures and indeterminate structures. So let me write here. Okay, so the first thing here is what we call the statically determinate structures. So we are going to see at least 3 components that will define what is determinate and what is indeterminate. Okay, so first is the equilibrium, and you will see how they are going to compare. Element, force, and deformation behavior, and then geometry. How would like the material or the body will deform. Okay. So suppose that we have a typical element. We have F, and then we have the area, we have the stiffness, the Young's modulus, and we have the length. And of course, in every axial deformations, this is all the elements that we need to calculate the elevation. So we have F, L, A, E. The E is equal to F, L over A, E. That's basically all the elements that we need for axial deformations. Now, what we need further is to analyze or to observe what will be the equilibrium. So suppose that maybe we have F here, F there, or maybe we have only F here and maybe we have reaction forces. And perhaps maybe in another case we only have one known element of force and there are 2 other unknown forces or reaction forces that we need to observe. And that will be how we can analyze the structure on the questions. So suppose that we're going to start with the statically determinate structures. Determinate means that throughout the diagram, we can see that we can solve all the forces and all the elements needed. Okay. So for example, we have here it's actually the same with our example before. This is from example in chapter 2. So we have two rods, different diameter, different length, and we have all the elements for the forces. We have this 10 kilometer, 30 kilometer, and of course we have some wall here, right? We have some wall which has a reaction force here. But since we know this, then we could still solve these questions. We could know what is the equilibrium. That's basically the statically determinate structure. So based on the statics, based on the equilibrium, we could know the reaction forces. That's basically the definition for statically determinate structure. So the question here says that the stress 1 and 2 is respectively were determined, basically based on all the area and all the forces, right? Okay, and then uh, the two element structure is statically determinate. The stresses are independent of the materials. So it's independent. And now we need to determine the UC. UC will be the displacement. The displacement for this steel or the rock. So we have E1 is 200, E2 is 70 GPa. So we can see that if we have elongation 1, elongation 2, these two, if we add, that will be our displacement. So we could write some. So before we start to work this exchange of deformations, always remember that we start with the expression elongation is equal FL over AE. Okay, this is every time you see any problem with the axial deformation, that is the formula that we are going to use all the time. Either maybe some of them, for example, we could in some cases to help analyze easily, we could relate to the stiffness or the force element, like F, the small f and a k, which I personally not really doing much on that part. I'm always using this to help understand the case. So we start with that, and then we see from the equilibrium, we could write here that we could see the cut down the rod 1. Let's say this is the rod 1. Okay, suppose that we cut this down. Okay, we cut this. Let me write with okay. So we have, this is 30 kilonewton. And we have another one which is cutting down the one here. This is having some PA over there. This is 10 kilonewton. This is going to be 30 kilonewton. And of course, from this part, we have take the sigma fx, and the f1 will be 10 minus 30, or 10 kilonewton minus 30 kilonewton, which is negative 20 kilonewton. And then if we cut the two, so maybe here's the cut. The same way we have F2. So suppose that this is going over there, F1. F1 plus okay, so this will be F2. So F2 equal 10 kilonewton. Okay, now we take the E1 is F1, L1 over A1 and then E1, and we can compute everything within this informations into the elongation 1. And still, since my suggestions, although we have this as a negative, and we know that this is on the left, so the right position should be going to the right, the F1. But since this is our assumption at the beginning, we still keep this as a same value and the same, just keep that as in the original. So then when we put the F1 here, we are going to include this negative just to help us navigate easily. If we change everything in the middle, maybe we are going to have wrong assumptions and then maybe a different results. So this will be equal to, so if we compute everything, this will be equal to negative 0.0955 millimeter, and E2 with the same idea will be having this. Okay. So the F1 will be shortened, we'll be having a compression, and the element 2 will having a tension, okay, because it's positive. And then we could take the total displacement. So we just add this two, which is going to be 0.0662 millimeter. Okay. Or maybe if you want to write completely, the A1 will be pi over 4 20 millimeters squared. A2 is pi over 4 15 millimeters squared. Okay, and then just put inside the equations. And don't forget the units. For example, the GPA, we can relate the GPA through the megapascal, because megapascal is Newton over millimeter squared, right? So we get right here, or maybe take thousands. This is MPa. Remember, this is going to be useful unit. Okay. So basically take all and then compute. Okay. So every time you have the total displacement, what you write is basically adding all the sum of this F and how many rods you have, how many elements you have, and just adding all this. Okay, so, oh, by the way, have you worked all the assignment? Okay. Should be, I think, today is the last day, and I think already finished, right? Okay, so for the midterm, When should we have the midterm? Now it's April 1st. Is 15 okay? So 8 and 9 I will give some all the practice for 8 and 9. So 3 hours practice and 15 will be the midterm, okay? So that means midterm will be chapter 1, chapter 2. Okay. Basic chapter 1 is every chapter. So basically chapter 2. Basically chapter 2 will include chapter 1 inside. Okay. Okay, 8 and 9. So but tomorrow I will have some example for this chapter 3, okay? Because we don't really have much time left. And I think since we are in schedule, so I think we can finish all the chapter 4 up until chapter 4 and adding maybe some sort of short chapter, either the equilibrium of beams, stress in beams, and or deflection in beams. So either of those 3. So after the midterm, we are going to have expected quiz that will be about the axial deformation, and the final will be axial deformation, torsion, that's the main part, and some topics on beams. Okay, on beams. If not, and if I think we need to have one more quiz, then the other quiz will be about the beams. Okay, and that can be quiz at home assignment. Okay, basically. But we are going to think that later. Okay, if I think the average is too low, then I need to increase. Okay, let's go back to the topics. So I think I just need 2 more example here from the textbook, and then tomorrow we can have a review on an example in the textbook. So this is so we have a weightless beam, AC, that is our beam. It's supported at an A by vertical column, so we have a column, and then supported by vertical rod that is attached to the to a leveling jack, that is a jack that can support the required load in CD, and it can also move the position of D upward or downward. And we have point B, which we applied our load P. It can be anywhere along the beam as long as we are in the range between 0 to 1. Okay. And then the purpose of the leveling jack is to keep the AC is going to be straightforward, or it is perfectly level. So basically it says that wherever the T, the AC will stay as it is, which means somehow this rod, it can be reduced in size, or it has some deformation, or this L2 will also change. That we have the D, right? We have the D, so it can be also changed. The positions can be changed, and this level can also be changed. So it's actually quite complex. So we first is we determine the stress 1, the actual stress 1 in the column, and stress 2, which is on the rod. So basically, all these questions, we need to typically solve one by one, so that we can solve the final question, which we need some information from question 2 and question 3. So first, we need to find the stresses in 1 and stresses in 2. The second is the displacement for A, and then the third one is displacement for the leveling jack. And then remember that because our leveling jack at D, it can keep the beam AC perfectly level, which means that we need to make sure that every time we have some changes, the displacement on C will be going to be equal to displacement of A. It gives you some clue for how to solve it. And then there's some dimension, and this is in the British unit or not in or American units. But supposedly it works the same way. So we have the P, we have L, we have the A1, A2. It's already in the area, so we don't need to calculate with the diameter. And we are given the same stiffness. So this material, they are the same material. 1 and 2, the same material. So basically, first is we are going to work out the diagram. So let me write here. So write the diagram. So based on the AC, that's our works. So suppose that this is AC. Here is we have let's say we have F1, okay, to simplify, and at C we have the F2. And then suppose that we have B in between here, and that is P. And since we have the range A is in between 0 and 1, which means if this is the whole total length will be L, then the fractions AB and BC will be based on the 0 to 1 or A, and also L. So let me write here as this will be AL, and this will be the L1 minus A. Okay, now we have 3 external forces in this diagram, and we have all the distances. Then we could start from the moment with respect to A or with respect to C, so that we can have in between, and we can just work those two to get the F1 and F2. So first we take the sigma of M. Let's say this is with respect to A, and then suppose that this is going to be positive that way. So we have negative F2 L, and then plus P AL, this is equal 0, and then we have sigma M with respect to C. So this will be negative F1 L plus or minus, right? PL1 minus A equals 0. I think I can make this as positive, all positive, right? And this can be works as F2L. And we can literally take in all the L. And using this information given, all the units and the numbers, the A is 0.4, so we could write that the F2 are 0.4 multiplied by 2 kips. This will be 0.8 kips. And F1 will be, this is 2 kips, 0.6, so 1.2 or negative 1.2 kips. Okay, so we get everything for F1 and F2. And we get the sigma F1 over A1. This will be negative 1.2 kips over 2 inch squared, which this is giving you the KSI. And since it's negative, this is compression. So every time you have the stresses, don't forget to let the information about whether it's tension or compression. Okay. So the 1 KSI, and this will be a tension since it's positive. So we have normal stresses, both materials, 1 and 2. Okay, now the second part of the question. So this is the first part. The second is the displacement, and we are going to use the FLAE. So for the first material, this will be F1, L1, A1, E1, and all the information are given, right? So we can just take that using the F1 from the first part. We are going to have the negative. This will be equal to negative 2.4 inch, and then E2 okay, of course you need to compute and just plug in everything into the equations. And E1, if you see from this part here, E1, the material 1, is basically the displacement of UA, but negative, right, shortened. And E2 is basically this and that displacement. If you see this displacement here, if there are something shortened on this side, which means that this is going to be over there, and this will be leveling the AC. So which means the E2, the elongation 2, will be the difference between these two displacements. So this will be UC minus UD. Okay. So here, E1 is negative UA, E2 will be UC minus UD. So UA will be 2.4, and the UA will be downwards, and then UC is equal to UA from the questions, also given the information on this UC equal UA, and UD will be UC minus E2. Minus the 2. So this will be 0.4 inch, and this is also going to be downward. So the final notes within this context or the questions. So to keep AC level for the given position of load B, it is important for leveling jack to support load 0.8 kips. While allowing the rod attachment move 0.4 inch. So basically, for the determinate structure like this, we can observe the element forces or the elongations based on the equilibrium. So whenever we have equilibrium that we can solve, and then basically this is what we call the regular default. Regular default. Okay, just a quick glance on what's next. Okay, there are one example, but I will skip for now. We'll return later. So I will go directly to these statically indeterminate structures to show you what is our expectations. So if we imagine the first condition, which we have done in the previous example, this is what we call a statically indeterminate structure. So we have, suppose that we have, for example, we have some reaction force here, but we know our forces B and C. EB, BC we know, and we can basically from the equilibrium we can get the whole thing, and then we can take into the elongation formula. We can have all the computation for the displacement. But for this one, if these two, they are having the wall in between, which means that we have a reaction force here and here, but we know that there is some forces that is applied in this point B. This is not easy to compute because this is something that we are not knowing. So we need to have what we call the compatibility equations. What is the best case for this to be worked at? For example, what will happen in this wall here? And we say that within this wall there is no elongations. And we can imagine that the elongation is 0 here. That is one example that might work. So that's what we call the compatibility equations. So we write here, always the steps are going to be, we start from the equilibrium, and then we have the element force distribution, or let me just sum up as this is the elongations itself, and then geometry of distribution. So here both ends attach to the walls. So the problem is the known information is only PB. The unknown will be PA and PC. Okay. So to solve this equilibrium, then if we imagine this is how it works. Okay. So imagine that there will be a displacement in the middle. So all the things we write first. This is our observations for elongations. And we need to add additional constraint. So what is the total constraint? If this is having the walls on both sides, so this constraint for the elongations, let's say we have the EAC, okay, the elongation here. Okay, so now this you need to make sure that you have very good sense in engineering. Imagine this is a wall. Okay? This is a wall. Okay? If we say the elongation from A to C, okay, can you agree with me that the elongation will be 0? Okay. Imagine this wall cannot be moved, right? So imagine that the wall stays as it is. So we could imagine that there will be a small displacement here, but the whole thing will stay as it is. So there will be maybe something going forward here, but there another reaction that is going to be cancel that out, so that the whole elongation will be still 0. And so that's what we call the compatibility equations. Okay. So this is additional constraint. Let me write here. This is the additional, not the total, additional constraint that we need to add to solve the equations. So to solve, we need these assumptions. We need these assumptions. So the elongation for the whole system, this is still E1 plus E2, but this is going to be equal to 0. So from here, we could imagine that the F1, L1, A1, E1, this will be equal to negative counterparts for the second material. And if we have the same material, we can cancel this out. The same cross section, we can cancel this out. So basically we have, and if we have the L, which is having some ratio, so F1, so it's stay with F1, L, and then F2, L2 will be 2L, So L will be cancelled out. So we have F1 equal negative 2 F2. Okay, now this is from the equilibrium, we get this. Okay, and then from the these three diagrams, we can get all the equilibrium for the PA and for the PC, since we know the ratio that we have relation between F1 and F2. So from here we get the PA. The PA is negative F1, and then here is F1 is PB plus F2. So we have F1 minus F2 is PB. And then here we have the PC, so F2 is equal PC. And then we have here, to make sure that we get the PB, this is, we can also write the F1 is equal 2 over 3 PB from the resulting from this equations. And then UB, the displacement at P, it can be, we can write UB as E1 or UB is negative E2. Depends on what we can imagine. So since we know the PB is going to the right, so this is also important here. So since this is going to the right, so we can imagine that the material 1 will have some extension, and material 2 will be minus. So if we imagine elongation 1 will be positive, but elongation 2 will be negative. Okay? So that these two, if we combine, should be zero elongation. Okay, I think that's all for today's class. I will give you more example maybe tomorrow how to solve the axial deformation, and I think more examples and more practice will help. And next week we can start by reviewing the chapter 2. Okay, so that's all. Let me give you the attendance.